In this video, I'm going to be talking about impulse, graphing, problem solving, and the conservation of momentum. The first thing we're going to take a look at is this force versus time graph. And this is a pretty common graph when you're taking a look at impulse. It is a force applied over a specific period of time, causing an impulse, which is a change in momentum, which for the most part is usually just a change in an object's velocity. So this sort of spike will look kind of common, and what you're going to find from this information is the impulse during this little chunk over here. There are two impulse formulas, mass times Vf minus Vi, and there's also force times time. Obviously, the second one over here is much more closely related to what we're looking at on this graph. So if you want the product of force and time, what you're doing is you're actually just finding the area. You're finding the area underneath the line, which is known as the area underneath the curve. So what you're going to do is you're going to find the basic area of a triangle, which is just 1/2 base times height. So I have 1/2 of my base, and be careful here, you're not going to put 5 because it's just 3 to 5. So the delta t, the change in t, is 2 seconds. So we got 2 here, 1/2 base, and then times my height, and it goes from 0 up to 15. And that would be my impulse. So 1/2 times 2 is 1, and then 1 times 15 is 15. So 15 kilogram meters per second is my impulse. I'll go ahead and put the delta P over here, the change in momentum, which is the impulse. So that is how you find the impulse using a force versus time graph. And then if you have some follow-up questions, you can go ahead and use that delta P for finding such things as the final velocity, initial velocity, or the mass. Okay, so let's take a look at our second part of our screen over here, which is a word problem, which is now separated from our initial graph. This is a totally different scenario. It has a 2 kilogram cart that's rolling at 3 meters per second, and that strikes a 5 kilogram cart going towards it at 2 meters per second. This causes the 2 kilogram cart to move back at 1 meter per second. What is the final velocity of the 5 kilogram cart? Okay, so as usual, especially when you have this much information and directional stuff, I'm going to start off with a diagram. All right, so what I did is I set up each of the objects before and after the collision, labeled with their mass, with the velocity, and then I made sure I had my arrows and my vectors to make sure I spotted anything that was going the opposite direction, which I'm calling to the left, and then making sure that's labeled as a negative. So the first way I'm going to solve this is using an impulse formula, and then I'll solve it one more time with a different method using the conservation of momentum and just mass times velocity. So the general gist of it is that the total momentum before the collision of the entire system is equal to the total momentum of everything after the collision. Now, all sorts of things happen to it, but that total of the entire system, these two carts, is going to remain constant for before and after the collision. All right, with that being said, let's take a look at the impulse of my 2 kilogram object. Okay, the impulse of my 2 kilogram object is just going to be using this right here because we're not dealing with forces and times. I have mass times a Vf minus Vi, so let's go ahead and set that up. All right, so I went ahead and set that up, and I have my mass of the 2 kilogram cart, which is going to stay consistent. And then it's VF minus VI. So here's my final velocity of -1 after the collision. So -1, and then minus my VI. That was my original velocity before the collision. And then I just have -1 minus 3, and then 2 times -4, and I have an impulse of -8 kilogram meters per second. So going back to what I said earlier, the total momentum of the system has to remain constant. So I know that if the 2 kilogram object has a change in momentum of -8, in order for the system to stay constant, the impulse of my 5 kilogram object has to be +8. So if one loses 8, that means the other one gains 8 in order to keep the total momentum constant. So let's go ahead and set up my information for my 5 kilogram object. I'm still going to use this same formula over here, times parentheses VF minus VI, and then I'm going to find my VF, my final velocity of the 5 kilogram object. There we go. I got my final answer. It is -2/5 meters per second. And the way I did that is, as I said before, the change of momentum of one object was -8. Therefore, the change of momentum for the other object is +8. And then I set that equal to m times parentheses VF minus VI. So it's minus -2, which is basically just +2. So I distributed that 5, which gave me 5 VF plus 10, subtracted 10 from both sides, divided both sides by 5, and then I got my final velocity of -2/5 meters per second. So that's using impulse in order to solve for the final velocity of an object. And now I'll go ahead and show you the way that I would typically use, which is just using the conservation of momentum and mass times velocity. As you can see, I got the same final answer of -2/5 meters per second using some momentum concepts just in a different way. So this is the way that I would more commonly use for a collision with a before and after. And all I did was simply take my masses and my velocities and slid them straight down. All I needed was momentum equals mass times velocity, took the momentum of both objects before the collision, set them equal to both objects after the collision. And as I already did before, I was very careful about placing negatives where I had things going in the opposite direction to the left. And then I just did the algebra from there and came up with the same number. So is there a right way to solve for this one? Not particularly. If you take the right numbers and you put them in the right spot, you can use different formulas to get to the same final result of -2/5 meters per second for your VF. So I hope that was helpful in helping you understand a force versus time graph, an impulse calculation, and a conservation momentum calculation. Thank you for watching and listening.